Woohoo. If you have any questions, that's a perfect moment in your life to ask questions about maths for economists and maths in general. So if something is not clear in lectures, classes, home assignment, then I'm listening.
I would like to ask about this Horvitz matrix and convergent time paths.
Okay. Basically, the idea is simple. The proof of Horvitz criterion is technical by induction. But basically, it's generalization of Viet theorem. So the question Horvitz, I don't remember how it's written in English. I think it's something like Horvitz. In Google, I don't remember honestly. Horvitz. No, I have missed T.
WITZ. It's W there, I guess, not V. I'm not sure.
Yeah, it's yeah. You are right. Yeah, I'm wrong. Yeah, like that. Okay. Horvitz criterion, Horvitz stability criterion. So first, the idea is very simple. Idea is very simple. Let's consider some differential equation, y prime prime plus some coefficient y prime plus a0, sorry, y is, let's say, equal to 0. I don't care. And imagine I give you the roots of characteristic equation. I say that root 1 is -3, and root number 2, because I have a second order differential equation, root number 2 is -7. And my question is time path isn't time path convergent? My question is time path converging for particular solution in that case? And the answer is very easy. Yeah, the answer is very easy. The answer says me that if I have lambdas, roots of characteristic equation, then I can build my general solution. General solution y of t will be equal to what?
C1.
Yeah.
-3 to the power of t.
We have not difference, but differential equation for the moment.
Oh, yeah.
So it's not difference, it's differential. Yeah, you are right for a difference equation when t is like discrete. Yeah, but you are wrong for differential equation. So you may write by analogy, you may use Horvitz criterion for difference equations. You are completely right in that sense, but I have stated it like that. So let's continue with differential. But you're right that you can do something like y t plus 2 equal plus a1 y t plus 1 plus a0 yt equals to 0. So you may create you may consider a corresponding exercise with difference equations. Yes, that's not a problem, but let's stick with my example.
Yeah, so it's e to the power of -3t.
Yeah, plus c2
e to the power minus 70.
Yeah, and obviously, without any Horvitz criterion, obviously, the limit of yt when t tends to plus infinity, obviously, this limit is equal to, I don't care about C1 and C2, because I have negative powers in the exponent, because they are less than 0. I don't care about C1 and C2. The limit is equal to
0.
To 0. So the answer is time pass of general solution convergent is yes. Okay.
Yes.
So how to check whether the time pass is always convergent? I need to understand whether all real parts of all roots is negative. If a real part is always negative, then I'm done. The general solution will converge to 0. If it's positive or positive real part with a complex part, then there will be no convergence for general solution. Yeah. And basically, what we need to check is the sign of lambdas, or to be more precise, sign of real part lambdas should be negative. This is the criterion. Negative lambdas or negative real part of lambdas. Lambdas like lambda 1 minus 2 plus 3i and lambda 2 minus 2 minus 3i. This pair of lambdas is okay, because I will have exponent minus 2t times some bounded cosine of 3t and sine of 3t. So this is also okay. So what I do care about the sign of real part of roots. And now let's go back to Viet theorem. Who remembers Viet theorem? If you have an equation like that, what does Viet theorem says? Who remembers Viet theorem?
Well, the sum of roots must be minus a1, okay?
Viet theorem. For this particular case, it says that lambda 1 plus lambda 2 should be equal to
minus a1.
Minus a1, and lambda 1 times lambda 2 should be equal to a2.
Yes.
So if I want lambda 1 less than 0, lambda 2 less than 0, then I want a1 greater than 0 and a2 greater than 0. Yeah, basically the same thing. So, c'est François Viet. François Viet. And basically, this is the Horvitz criterion, that a1 and a2 should be strictly positive. And Horvitz criterion just generalizes that idea to bigger number of to bigger order of differential equation, to higher order of differential equation. So if we have just second order differential equation, then Horvitz criterion is just exactly Viet theorem and the requirement that all lambdas should have negative real part. If we have a third order differential equation or fourth order differential equation, then the Horvitz criterion is just the same thing, but applied to like but basically the idea is here, and in general, what we have in general. So the proof is technical, and it's just by induction. You need to so let's consider an example like, so what is a Horvitz matrix? Yeah, Horvitz matrix. The idea is simple, it's just Viet theorem. And in general, we have a differential equation like that. Let's say H0 times Y. I don't like to write in general, but okay, let's write in general. Yn, that's a nth derivative, plus H1 times Y n minus 1 plus H2 times Y n minus 2 plus we have H n Y equal to 0. We have a differential equation like that. And let's imagine that H0 is just 1 or positive. So we really care that let's simplify it in the form that H0 is greater than 1, is positive. We may always make it equal to 1 just by dividing by H0. And so we construct the following matrix. We construct the Horvitz matrix. How it is constructed? The big Horvitz matrix. There are a lot of mnemonic rules. I prefer, because the proof is tedious. So it is not easy to just recover the proof every time when you forget it. So my mnemonic rule is the following. I just write H1, H2, H3 on the diagonal, like H1, H2, H3, H4. The last one will be Hn. You just, step 1, you just fill the diagonal of the Horvitz matrix. You just fill the diagonal, and then you go down in every column. So you decrease and increase. So you fill every column by column. So my way to memorize Horvitz matrix is the following. So you just write H1, H2, H3, Hn on the diagonal, and then you just fill every column in maybe it's from. So the only thing that it decreasing. So that's the only thing is one decreasing indices. How to read the indices in each column. So the Horvitz matrix is it's H1, H2, H3, Hn, and then you decrease the indices H0, and then you fill with 0, 0, 0, 0. What is decreasing H2? I start H2. H1, H0, 0, 0, 0, and I go up. It will be H3. If I continue with H3, H2, H1, H0, 0, 0, H3, that continues H4, H5, and so on. And basically here I have 0, 0, 0, 0, 0, and so on. This is the construction of Horvitz matrix. And Horvitz matrix should have all corner determinants greater than 0. So real parts of all lambdas are negative. That means for all I, real parts is, or maybe it's better to write k. That means for all k, the corner principal minor is strictly positive. Okay. Yeah, the idea is clear.
Yes, yes.
So basically, it's generalization of Viet theorem. So we need all negative lambdas, to be more precise, all negative real parts should be, all real parts should be negative. And that means that all determinants of Horvitz matrix should be positive. Why? Basically, it's Viet theorem. You know that if you need both roots of quadratic equation to be negative, then you want both coefficients in Viet theorem to be positive. So basically, that's why inversion happens. So let's even state it with, so let's consider two particular cases. Case with quadratic and cubic characteristic equation, and I think that's enough. So you just go on with a higher size of matrices, but it's boring. So I will consider the case of 2 by 2 matrix. So if I have an equation like that, y prime prime plus 6y prime plus 7y equals to 0, Viet theorem says, oh, lambda 1 plus lambda 2 is -6. Lambda 1 times lambda 2 is 7. So lambda 1 is negative, lambda 2 is negative. So time pass is convergent. And what does Horvitz criterion say? So this is H0, it is 1. This is H1 is 6. It is H2 is 7. So I build Horvitz matrix. First of all, I start with these numbers on diagonal. It will be 6, 7. Then this is like, so in the first column, I need H1, H0. In the second column, I need H2, and because I have no H3, so it's 0. So H1 is 1, H2 is 0. So delta 1 is just 6, is positive. Delta 2 is 6 by 7, is positive. And basically, time pass is convergent. I have the same conclusion. Okay.
Yes, okay. Yeah.
And to the 3 by 3 case, basically, if you'd like to go to the proof, it's a little bit boring. We can, but if you'd like, but I think it's better to.
No. I understood the general idea. Thank you.
The idea is to generalize Viet theorem. So let's consider 3 by 3 case, and if you like, I will try to point you where we have the solution. Maybe there is something intuitive, but I don't know intuitive. So that's done by induction. So you start that for case 2 by 2 is it is just the Viet Theorem, and then you make induction on the number of roots of characteristic equation, and you factorize your matrix in complex field. Okay, let's consider the case 3 by 3. I will try to, because I don't know the intuition behind this. So for me, just a technical statement that is generalized Viet theorem. Maybe there is some intuition why all coefficients, all determinants should be positive, but I'm not sure. 3 by 3 case. Let's provide an equation y prime 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 plus 2y prime prime plus 3 y prime plus 7y equals to 0. So h0 is 1. This is h1. This is h2. This is h3. So I create a 3 by 3 Horvitz matrix. First, I write these numbers on the diagonal, like 2, 3, 7. And then I I basically have 1, 2, 3, 7. I just put it like these numbers 1, 2, 3, 7, like in a column. So it will be in the decreasing order, like that. And then I just like slide this column by applying it. So I will have 1, 0 here. Above 3, I have 7, and below I have 2. Above 7, I have nothing. Basically, that's all. What is delta 1? Delta 1 is 2, is greater than 0. I'm happy. Delta 2 is 2 times 3 minus 7 is negative. I'm also happy. I just say that I don't need to check delta 3. I can calculate it. Obviously, you should be able to find the determinant of a matrix 3 by 3, but we don't care anymore because there is at least one lambda I with real part positive. And if we have, so for this equation, we in general have 3 lambdas, 3 solutions of characteristic equation. And if at least one is positive, then we can be sure that there is a solution with divergent time path. There is a solution of our differential equation with divergent time path. So basically, that's our answer. Okay. Any questions about the construction of Horvitz matrix?
No.
So basically, it's just a technical generalization of Viet theorem. I have intuition like that. So sometimes a long time ago, I have I have worked with the proof, but I don't remember details. Any more questions about classes, lectures, differential equations, difference equations, home assignments, anything? You are welcome.
And I have a question about number 5 from home assignment, last home assignment, about optimization.
Let me open it just a moment. Just one moment. I will. Ooh. Then I go here. Okay, it is the last one is 20, yeah?
Yes.
It was 19, I guess. It was 19.
No, 19, yes, thank you.
19. Yes. Ah, right. Yeah. Okay, my advice, big advice, big advice. I will write it in big letters. Twice. Use graphical approach with two variables. So my strong advice, always use graphical approach with two variables. Even if you have an explicit requirement, use a Lagrange multiplier method. Just go with graphical approach. And then if you are not obliged to use Lagrange multiplier method, then probably you are done. If you are obliged to use some particular method that does not that you are not prohibited to use graphical approach, even if you are required to use the Lagrangian method. So basically, first point, use graphical approach. So if you are not obliged to use Lagrange multiplier method, then probably you are done. Probably you don't need even to write first order conditions. But if you are required, then use the general idea that in Lagrange multiplier method, you have a beautiful equation that lambda times dl d lambda should be equal to 0. Yeah. Use this idea. If so, what I'm pretending that if you don't need to use Lagrange multiplier and you have two variables, just go with graphs. If you are required, then do not forget about this idea. What is the practical implication of this idea? If dl d lambda is not equal to 0, that means inequality is non-active, then lambda should be equal to, so what is the meaning and practical use of this equality? If inequality is non-active, then lambda, according to that equation, should be equal to, be brave,
0.
0. So that's all we need to solve such problems. So I will solve something that is like problem number 5, but not exactly problem number 5, but something. I don't recall the deadline is already. If the deadline is already passed, then I can solve the number 5 exactly.
Yes.
If the deadline, I don't remember because
It passed. So. Yeah.
Okay. If it passed, so okay, let's go exactly with the number 5. So let's go exactly with number 5. We have w y squared minus 3x. Xy is less than 6. 0 is less than x less than 5. 0 is less than y less than 3. Okay. Yeah, I have everything. I have. That's a question A. Just find the maximum and minimum. And B, how will the answer change? Answer change if the right side of each constraint, if we add plus 0, 1 to right-hand side of every constraint. Okay, that's the text of the problem. So my first advice, I have 2 variables. I go with plots because sometimes, and this is exactly the case, in this example, we don't need even Lagrange multiplier technique at all to solve it, but it's a requirement in the text. So first of all, I have 2 variables. That's axiom. If you see 2 variables, go with plots. So that's the main idea I'd like to push here. Okay, so I go with plots. Ooh, I can draw 1, 2, 3. So I will draw them. 2 and 3 is just a rectangle. Yeah, x, y. So it's just a rectangle. 5, 3. Yeah, I have already drawn constraints number 2 and number 3. Okay, x, y equal to 6 is just, we know that curve is 6 divided by x. So it goes something like, the first curve goes something like that. Yeah. Here I have 6/5. Here I have exactly 2. Yeah. And this is the curve number 1. Where is the feasible region? The feasible region is that triangle or that boot. Yeah. What is the feasible region? The boot or the triangle?
The boot, yes.
Yeah, this boot is a feasible region. Yeah, this is the feasible region. Okay, I have drawn feasible region. Now I continue with level curves of my function. So I have a function y squared minus 3x. I draw level curves. So I just make y squared minus 3x equal to c. So x is basically y squared over 3 p minus c over 3. Yeah. It's a parabola. Yeah. I can, so it goes something like that. And by choosing C, I can move this parabola. Oops, wrong. Should. Yeah. So by choosing C, I can move this parabola to the left, to the right, as I wish. Bingo. Pam, 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 pam. So what is the, if I increase C, my level curve moves to the left. Yeah. Shifts left. Yeah. Because I have minus C in level curve equation. And if I decrease C, my level curves shifts right. So basically, I can find two extrema. One will be maximum C when it is the last moment when my level curve touches the boot, the feasible boot. Yeah, it's okay. So I have 2 points. The leftmost blue curve is this. So I have A star, that is one extremum, and the rightmost curve is this one. I have B star, that is another extremum. So I understand immediately, without Lagrange multipliers, just from plot, A star is 0, 3 is the leftmost curve. So it's maximum C. So it's a global maximum. And B star equal to 5, 0. It's the rightmost curve. It's global minimum. So in that case, everything is solved graphically. Any questions for the moment?
But
No.
Yeah, the problem is that sometimes on London exam, they have an ugly requirement that solve using that method. Personally, I hate this tradition. I don't like it at all. So I prefer a problem that cannot be solved graphically, and you need to introduce Lagrange multiplier method because you cannot solve it otherwise. I prefer a problem like that. But on external exam, sometimes you have at my own opinion, it's a bad tradition, but it's a tradition that sometimes on external exam, you have a requirement, solve using that method. So you're not obliged to use only that method, but you're obliged to use the method in the text of the problem, but you may use other method. So we have copied this tradition to prepare you for the exam, but personally, I hate it. I think that authors should create problems where the method they would like to test is either the unique way to solve it, either the fastest way to solve it. And so if I know the method that authors suppose, then I win. And so I'm free to use any method, but the design of the problem is favorizes the use of correct method. In our case, so basically we have followed the tradition of London exam, but I'm personally against it. So it's my personal opinion that it's a bad tradition to do like that, but that in English tradition. So okay, we are forced to use Lagrange multiplier method. Okay, so how can I combine? So basically, it's a stupid game. Now we know the answer, and we will combine the known answer with Lagrange method. Okay, we are forced to use. That's stupid, but we are forced to use Lagrange multiplier method here. There are problems when we are not forced, but it's a unique way to solve them. So it's all very, very, very good method, very good way. Okay, so what can we do? We know that from the plot, I can use the plot. That's not a problem to use the plot. Okay, from the plot, I conclude that my this inequality is never active. Yeah. So my inequality is never active. And basically, so I have how many inequalities? So let's write them. 0 less than x. X less than 5. x less than 5, y greater than 0, y less than 5,
y less than 3.
sorry, it's less than 3, xy is less than 6 as far as I remember, yeah? Honestly speaking, I have 5 inequalities. I need to introduce 5 lambdas. Whoa, I'm scared. 5 lambdas. Okay, but from the plot, I see that inequality number 5 is never active in the optimum in point A or point B. That is never active. Number 5 is not active. Not active. So I may replace xy less than 6 by xy strictly less than 6. In that case, the corresponding lambda is 0. But if corresponding lambda is 0, when I write Lagrangian function, I can completely ignore inactive inequalities. So if from the plot I'm sure from the graphical analysis of the problem that some inequality is non-active, then I just ignore it in the Lagrange multiplier method. So let's continue with this simple idea. So now I will not use that one. And let's search for the let's say for maximum. Yeah, let's find maximum. Let's find maximum using Lagrange multiplier method as we are forced from the problem, from the text. Okay, we are forced to use inferior method in this problem. So sometimes Lagrange multiplier method is, you cannot proceed graphically and you are left with Lagrange multiplier method. So in that case, it has advantage. In this particular problem, graphical approach has advantage, obviously. Okay, let's consider maximization of y squared minus 3x subject to 0 less, x less than 5, y less than 3, y. Let's keep the order the same. So we know that this is not active. I have a y. So I will copy my boots. Maximum is here from graphical approach. Yeah, maximum is here. But let's imagine that we are not completely sure whether the maximum is exactly here, or maybe the maximum is here. Yeah, maybe it's here, so we are not sure. And so I say that I'm sure. So basically, it's a little bit artificial in this problem because I know the solution. And so I play just to satisfy the authors of the problem that I know the Lagrange multiplier method. Believe me, I'm just proving to authors of the problem that I know Lagrange multiplier method. That artificial task, I hate doing like that, but okay, we are required. Okay, I see that this is not active. No, sorry, this is active. Yeah, this is active. This is not active. This is not active. This is active. Yeah, at my optimum A star, this is active, that is active, and all others are non-active. Okay? Yeah, that's clear. Anyone with me?
Yes.
So I understand that it's stupid. I'm just pretending that let's forget about something about the solution. Yeah. Let's say we know from the plot that the maximum is this point, but let's introduce artificially some doubt. Let's say we are not sure whether this is active. We are sure that it's active, but let's think, oh, we didn't know. So let's introduce some doubt. In my case, I'm using partly information from the plot that constraint number 2, 3, and 5 are not active. 2, 3, and 5 are not active. And then I just write them like x is strictly less than 5, y is strictly less than 3, sorry. 0 is strictly less than y, and xy is strictly less than 6. So when I construct, so I have doubts only in the first, and so this is one we are not sure. We pretend that we are not sure. We play a game. So I say, okay, these are not active. I do not check in DCQ. So I check in DCQ only for the first one and for the last one. So if only first one is active, and I have 1, 0, it's full rank equal to 1. If I have only number 4 is active, 0, 1, rank 1. If both are active, so it will be 1, 0, 0, 1, rank is 2, in DCQ is satisfied. So from the plot, I have used the idea that 3 inequalities are not active, and I have forgotten about the other 2. I just say, okay, let's use Lagrange multiplier. Let's simplify my problem. Let's say I know from the graphical analysis that 3 inequalities are not active, and then I continue my analysis. Okay, so I will introduce a Lagrangian function. We need to maximize y squared minus 3x plus lambda 1 times x minus 0 plus lambda 2 times 3 minus y. Okay, I have created a Lagrangian function with only 2 constraints, because for other 3 constraints, I know that they are not active. And then I go on with first order conditions. Okay, what are the first order conditions? So I have left only 2 constraints. So inactive constraints, I have thrown them basically out. What are the first order conditions? dl with respect to dx should be equal to what?
0.
0. dl with respect to dy should be
2, 0.
0. dl with respect to d lambda 1, basically that's x1, that should be greater than 0. dl with respect to d lambda 2 is 3 minus y, should be greater than 0. Lambda 1 times dl d lambda 1 should be 0. Lambda 2 times dl d lambda 2 should be 0. And I need my non-active constraint. So I just copy not non-active constraint. I need them copied. So they are basically xy is less than 6. What else? X is less than 5. And y is greater than 0. 3 non-active constraints I have copied. And something more, lambda 1 is non-negative. Lambda 2 is non-negative. So basically, these are first order conditions. Okay. For maximization. Yeah. Do not forget that the one of the difficulties with Lagrange multiplier approach that there are a lot of difficulties. First, we introduce two more variables. Second one, we need to do it twice. Once for maximization and second time for minimization. Yeah. Okay.
Okay.
Let's solve it. dl dx is dl dx minus 3 plus lambda 1 is equal to 0. Yeah, that's fine.
Yes, it's fine.
dl dy, it's 2y plus minus lambda 2 is 0. Okay, so I have x is greater than 0, 3 minus y greater than 0, lambda 1 times x equals to 0, lambda 2 times 3 minus y equals to 0, lambda 1 is greater than 0, lambda 2 is greater than 0, and just I copy non-active constraints. Xy is less than 6, x is less than 5, 0 is less than 1. I have all these constraints. Oops. It's the lowest order of my sheet. So let's go on. Okay, I completely see the value of lambda 1. Yeah, lambda 1 is 3. So I know that x is 0. Okay, so from these, I conclude that lambda 1 is 3. X is exactly 0. Yeah.
Yes.
From that one, I conclude that lambda 2 is equal to 2y. I can plug into that equation. I have 2y times 3 minus y is 0. So I have two subcases. Y is 0 and y is 3. In that case, lambda 2 is 0. In that case, lambda 2 is 6, I think. And we need to check that this is not okay. And bingo, I have one candidate for maximum. Why it's not yet maximum? Because I need to check sufficient conditions. Yeah. So my candidate, we are not surprised because we have solved it graphically beforehand. So x is 0, y is 3, lambda 1 is 3, lambda 2 is 6. So we have a candidate for maximum. Let's check second order conditions. Yeah. Okay. So I understand that it's a little bit stupid, but you may encounter a situation like that on external exam. Graphical analysis is sufficient to solve the problem, but it's written in the text, use Lagrange multiplier. I don't know why they do like that. I disagree strongly that I think that's a bad style of problem. But we need to prepare you for not only to something reasonable, but something unreasonable too. Okay, so I understand completely that that's a little bit stupid, but we are interested in your high result on external exam. So I'm sorry, but that's what you can encounter. Okay, we go on to with second order conditions.
Yes.
So okay, what we do with second order conditions. So let me copy the values. X is 0, y is 3, lambda 1 is 3, lambda 2 is 6. I will just copy my Lagrangian function because I need Hesse matrix for it. Basically, I have what I'm doing. I'm solving the problem graphically, plus I'm proving to the authors of the text that I know Lagrange multiplier method. So I'm done. Okay, how we can work with sufficiency conditions? Strategy 1. We can use Weierstrass theorem. Weierstrass theorem. Feasible region. Our boot is compact. Function is continuous. Our y squared minus 3x is continuous. So Weierstrass theorem guarantees us that we should have at least one maximum, at least one minimum. At least one maximum, at least one minimum. We were searching for maximization, and we have found only one candidate. If we have found only one candidate, then it is maximum. So we have one candidate for maximum. That's our point. X is equal to 0, y is equal to 3, lambda 1 is equal to 3, lambda 2 is equal to 6. Then, according to Weierstrass theorem, this candidate should be maximum. Okay? Any questions about Weierstrass theorem?
No.
Strategy 2. I prefer graphical approach, Weierstrass theorem. I always try to avoid something complex. So sometimes it's unavoidable. Yeah, sometimes Lagrange multiplier methods is a hammer at our last resort. So if I can solve it before applying our mighty hammer, then okay. But sometimes we are graphical solution fails because we have 3 or 4 variables. Weierstrass theorem is not applicable because we have unbounded region or something like that. In that case, I go with Lagrange multiplier method with Hesse matrix. So I prefer simplest methods if they are possible. If they are not possible, so okay. So how I construct Hesse matrix? So in my case, I have already solved it. I have already solved it a long time ago, even before Lagrange multiplier approach, yeah, because I have used graphical approach. But if we are forced to use graphical, if we are forced to use Lagrange multiplier method, okay, we build a Hesse matrix only for active constraints, okay? Only for active constraints. But in our case, we have a problem because which constraints are active? X. So let me recall all the constraints. 5, Woohoo. So that one is active, that one is non-active, that one is non-active, that one is active, that one is non-active. The problem is that in this case, I have two active constraints. Yeah, I have two active constraints. And my approach with Horvitz Matrix failed. Because if you remember, I need to check n minus q minors. I need to check n minus q minors, where n is a number of variables. And k is a number of constraints. And this strategy with Horvitz Matrix is applicable. Horvitz Matrix is applicable only if n minus k is strictly greater than 0. In my case, n is 2. I have two variables x and y. K, the number of active constraints, is 2. Where is the first one? Where is the second one? 0 is equal to x, y is equal to 3. So in my case, this approach is not applicable. But in the case Horvitz Matrix is applicable, I just calculate n minus n. So basically, we have solved maximization problem twice. We have solved it without use of Lagrange multipliers, and we have solved it with Lagrange multipliers plus Weierstrass theorem. So we have solved it twice. And then we do the same thing, but for minimization problem. If we have minimization problem, then what shall we do? So the same for minimization problem. First of all, if we are not required to use Lagrange multiplier approach, then we are already done. We know that the minimum is the rightmost position of level curve. It is parabola. So this is the point of a minimum. X star is 5. Y star is 0. So if I'm not required to use Lagrange multiplier method, then bingo, I have done using graphs everything. If I'm required to use graphical approach, once again, from graphical approach, I can use this. So if we are required, then use this big idea that Lagrange multiplier times left-hand side of inequality should be 0. That means either lambda is 0, either inequality is active, either both. But that cannot be simultaneously that lambda is positive and inequality is non-active. So basically, I see that, so I combine, if I'm required to use Lagrange multiplier, then from graphical approach, from plot, so what to do if you are required to use Lagrange multiplier approach. From plot, find non-active constraints. From plot or otherwise. So that's a great idea if you have some intuition why there may be some other good reasons that inequality is non-active. So for example, what may be other reasons, even if I have 3 variables and I have 2 inequalities, One is like that. And the other one is like this. So I see that if I have two inequalities A and B, I see that A follows from B. If B is satisfied, then N is satisfied. So I understand that A is not active. So you may find non-active constraints not only on plots, but by some other logic. That's okay. And if you have non-active constraint, then the corresponding lambda should be equal to 0. And we just do not include that constraint in a Lagrange function. Okay? So basically, should I repeat the same thing for minimization, or everything is clear?
It's clear.
Let's just check that we can state first order conditions, and we will not go further, but let's state first order condition and let's check in DCQ. So from plot, I see that xy is less than 6. So once again, where is my B? So I see that this constraint is not active. That constraint y is less than 3. And I see that x is greater than 0. So I see that I have 3 non-active constraints, and I will not include them in Lagrangian function. I will not introduce lambda for them. That's a very powerful idea. Lambda times dl d lambda is 0. That's a very powerful idea. And so I need to minimize y squared minus 3x subject to x may be 5 or less than 5, y greater than 0, and from some intuitive reasoning or from the plot here, I see that I have 3 non-active constraints. So when I will check in DCQ, I will check in DCQ only for these 2 possibly active constraints. I play a game to show the authors that I have mastered Lagrange multiplier method. So in DCQ, if only x, only first one is active, then I will have 1, 0. Jacobian matrix rank is 1. If I have only constraint that y is 0, then I will have Jacobian matrix 0, 1. Rank of Jacobian matrix is 1. If both are active, then I have Jacobian matrix identity matrix. Rank is 2. And in DCQ is satisfied. In DCQ holds. Then I move on to first order conditions. Personally, I prefer to always deal with maximization. So I will go from minimization to maximization. I will just say that I need to maximize 3x minus y cubed. Then basically the same thing to minimize y cubed minus x 3x. I like maximization problem. Okay, plus lambda 1 times 5 minus x plus lambda 2 times y minus 0. And let's write first for the condition and let's finish. So basically, because the procedure is exactly the same, once again we will find one suspicious point. Once again, Weierstrass theorem will be applicable. So let's write all first order conditions. dl with respect to dx is 0, dl with respect to dy is 0, lambda 1 is non-negative, lambda 2 is non-negative, dl with respect to d lambda 1 is non-negative, dl with respect to d lambda 2 is non-negative, complementary slackness condition lambda 1 dl d lambda 1 is 0, lambda 2 dl d lambda 2 is 0, plus non-active constraints, we just copy them. So this will be the full list of first order conditions. And when, once again, we will add Weierstrass theorem. Okay.
Okay, and what about the second point?
Which one? Second point.
The second about if we increase constraints by 0.1.
Okay, let's move on. We will work with maximum only. The same thing holds for minimum. So if we increase every constraint by a small number, so we assume, so basically, so there are two solutions. One is exact. So we need to redo the problem with lambda equal to 0, with right-hand side equal to 0, 1. So that's possible strategy. Yeah. In our case, it's feasible because everything is on the plot. But if we have something complex, so what? Yeah, you're right. I forgotten about that point. Yeah. Okay. Point B. What happens? What happens with maximal value or with the optimal value? What happens with optimal value with maximum? Because we have solved maximum. Okay, what happens with maximum? But for the minimum, the logic is the same. If we increase right-hand side, every right-hand side by 0.1. So there is exact answer, and there is fast approximate answer. So if we need exact answer, so we just change our boot, how our boot will change if we increase every right-hand side. Yeah, in original problem we have so the right-hand side is we add plus 0, 1 here, plus 0, 1 there, plus 0, 1 here. So if we look for the exact answer, so we need to increase every right-hand side by 0, 1. What will happen? The boot will increase. So we will have bigger boot, big foot, bigger boot for big foot, X and Y. And if we are searching for the new maximum will be here. This is the position of new A star. Yeah. And if we like an exact answer that can be obtained in this case, we can go with exact answer. That's not a problem. X star is 0, Y star is that will be 3.1, and optimal value will be y squared minus 3x. It will be 3.1 squared. So that's an exact answer. If we go with fast approximate answer, so we know that we can go with like delta optimal value is approximately, if we are lucky, it will be approximately dl to d parameters times delta parameter. In my particular case, that inequality was inactive, so lambda was 0. That inequality was inactive, so when I change it by 0.5, lambda 0 times it will be 0. Okay, and that was active. So it will be the change of optimal value. My Lagrangian function looks like, so let us go back to the first one. Where it is, yeah. So I will introduce my parameter p is introduced here. I have 3 plus p, and so dl with respect to dp is just lambda 2. So if I add the parameter p here, the derivative of Lagrangian function with respect to that parameter is just lambda 2. Okay, is that clear? If I go not with exact solution, in that simple case, we can have exact solution. But in a very complex case, when the exact solution is not feasible, we can do an approximation. Yeah, any question? We go on.
Okay, everything's clear.
And then approximate answer in my case, because I have lambda 2 times 3 plus p minus y, dl with respect to my parameter is just lambda 2, and my delta parameter is it was 0 and it was 0, 1, so 0, 1. So my approximate delta of optimal value is approximately lambda 2. If I'm not mistaken, I have copied somewhere. It was 6. Was 6 by 0, 1. Okay. And it's 0, 6. And let's compare approximate value with exact value. The old optimal value was 3 squared. It was 9. The new exact optimal value is 3.1 squared is 9 plus 0, 0, 1 plus 3 times 2 times 0, 1. And it's 961. And approximate optimal value according to approximate way is old one, 0 plus 0, 6. So if we use approximate way, which is based on envelope theorem, we just calculate dl with respect to d parameter and we multiply by delta of parameter, then delta is equal to 0.6 of optimal value, and the true delta is equal to delta to 0.61. Okay, in our case, both solutions are feasible, the exact one and the approximate one. In our case, even the exact one is much faster because we have graphical approach and so on. But the approximate is quite good. The approximation is quite well. So we are off by 1/100. Any
Yes,
questions?
thank you. It's clear now.
Oh, the time is up. Okay, basically that's all. I'm always happy when you have questions because that's much better. Okay, so see you next time. If you have any questions, just don't be shy and ask them. Be brave. Have a nice day.
Thank you.
Thank you. Goodbye.
Goodbye. Bye.
Thank you.
Sorry, I have missed something in the chat. Oops. Thank you. Okay. Yeah. Okay. Bye bye.